Hello everyone, welcome to this training session on how to properly plan your compressed air system. My name is Andrew Williams and I am the Territory Sales Manager, and I'm here with my colleague Naitik.
Hello everyone, my name is Naitik and I am a Territory Sales Manager at Topring as well. Today, we're going to talk about some important things to consider in your system. Among other things, we will look at the materials and situations in which an aluminum system is the best choice. We will also review the design steps and the importance of properly planning your air system. Lastly, we will look at the advantages of Topring's PPS line and how this system can make your system even more efficient.
When it comes to conventional materials used for compressed air systems, steel is often the first one that comes to mind, whether it is black or galvanized steel. Steel has been used for many years and continues to be used due to the affordability of the material. However, it is a material that has a number of disadvantages. One of the most important is the fact that steel oxidizes or rusts. This phenomenon will cause two problems. The first is that the inner wall will become very rough and cause pressure loss and turbulence. The other problem is that the rust that forms will break off into particles and contaminate the entire system. With galvanized steel, oxidation is a little slower, but still inevitable. Tubes that are hot dip galvanized when they are new, as a result, they are very rough on the inside, which reduces their performance. Also, one of the worst drawbacks of steel is its weight. We all know that steel pipe is heavy and very labor intensive to install. Installation can become a long and complex process because for each connection, the pipe must be cut and at least 2 threads added. This also makes the system difficult to modify later on.
Andrew, let us not forget, threading also involves the use of cutting oil, which will end up contaminating the system.
Of course, it is a contaminant that can cause problems in the system.
Another drawback of using steel pipe in general is that the screw-in system with the sealant is the least airtight method available in the industry. This means there are always leaks, and leaks mean higher operating costs.
Copper and stainless steel are 2 other materials used in the design of systems.
Copper is a material that is still widely used in the field of medical gases. Why? Well, because some pharmaceutical industries still require it, and in many cases, it is the only material that meets their standards. However, copper is a material that we would like to avoid. Copper is much more expensive than steel. It is also heavy to handle, and its biggest drawback is that it requires soldering to connect it together. This means a complex job site with significant safety precautions. In addition, the welded connections make it difficult to modify this type of system. Another material which is used less frequently is stainless steel. In theory, stainless steel is an appealing choice because it is resistant to many things. However, in practice, it is heavy, very expensive, and even more difficult to thread than black steel.
Even in industries where chemicals are used, such as paper mills, we don't necessarily have to use stainless steel. The majority of the time, you can operate with a much more economical piping system. So, in theory, stainless steel is a good choice of material, but in reality, it's not often used.
And then there's aluminum. This material was introduced into the market a few years ago due to a decrease in the cost of raw material. It was found that aluminum has many advantages and is also affordable. Unlike other systems, aluminum is very easy to install. It is much easier to transport and to mount on the ceiling for installation due to its light weight.
To give you an idea of what Naitik just mentioned, an aluminum tube is 3 to 4 times lighter than the equivalent steel tube. In most cases, you need 2 installers and a boom lift just to install a steel tube, whereas you can operate with only 1 person for an aluminum tube.
That is right. A big savings in time and manpower, and that has a major impact on the cost and timeline of the project. We saw earlier with steel that its rough finish creates turbulence. However, aluminum tubes are smooth, which reduces pressure losses across the system. In addition, the fact that aluminum does not rust eliminates all problems related to oxidation. Last but not least, unlike all the other materials, aluminum does not require any threading or welding, and its installation method ensures an optimal seal.
When you compare the overall cost, not only for the purchase and installation, but also for the operation and maintenance of a steel system versus an aluminum system, you will find that aluminum is more economical. Sometimes people will tell us that steel is cheaper. I would like to draw your attention to this part of the graph. Although the material cost is lower for threaded steel, When you include the installation costs, the aluminum system becomes more economical. So, from the day you complete the system installation, before you even use it, aluminum is cheaper than steel. Let us move on to the second major component of our training: how to properly design a compressed air system. The first step in your planning is to determine the nature and location of the workstations. Let us take the example of a municipality that is planning to build a new water system. They need to know where the streets and houses are in order to get to the right amount of water to the right place. It's the same principle with an air system. The very first thing is to know where each workstation is going to be located and how much airflow is going to be used there.
Other important things to consider are the size of the building, the location of the system and compressor room, the number of floors, and the possibility of future expansion. This is not always taken into consideration at the beginning of the project, and it can have a major impact on the performance of your system.
Yes, this is often a forgotten step. In a few moments, we will show you how you can factor in future expansions up front.
The next step is to estimate the air requirements for each application. The first thing to consider is the number and type of equipment requiring air that you will be using at each workstation, as well as the amount of air consumption. Some tools like impact wrenches use a lot of air intermittently, whereas other equipment like paint guns use air for extended periods of time. So, to calculate the actual air consumption of a piece of equipment, you need to estimate the percentage of time it uses air. For example, you have a half-inch impact wrench that consumes 30 SCFM. If this wrench is used 10% of the time, it consumes an average of 3 SCFM. Repeat this calculation for each piece of equipment. Then apply your results to calculate the consumption of each subsection and the entire system. Sometimes multiple sources are drawing air from the system at the same time and you want to avoid an excessive drop in pressure. To be on the safe side, you should always incorporate a safety margin of 25 to 50% to the total volume of air consumption.
In addition to volume, another aspect to consider is the quality of air required. It is recommended to process the air with filters, dryers, and water separators from the compressor room. This also can be done at the individual workstations with filter regulators and modular dryers. Now ask yourself, what air quality do I need at each workstation? You need to provide satisfactory air quality for your system at most workstations. Eventually, some departments and workstations will need better air quality. In some cases, the conditions in the workplace will need to be taken into account. For example, in a freezer, the air must be very dry to avoid the formation of ice. In this situation, you could add an additional point-of-use air dryer to counteract this effect. So you need to know the temperature of the environment where people work. And lastly, when it comes to compressors, you need to know the horsepower, volume, and location of your current or future compressor. You will sometimes use more air than your compressor can supply, so it is very important to have at least one tank, and you may need auxiliary tanks at remote points in your system.
Now, let's talk about configuration. You may have seen systems that are configured this way. At Topring, we like to call this configuration the octopus. As you can see, the octopus is a maze of random connections that has formed as machines have been added and expanded. This type of configuration has several bottlenecks that impose excessive restrictions on airflow and cause large pressure drops. Unfortunately, these systems are all too prevalent today in organizations that have grown and not properly planned ahead. Andrew, if the octopus is the worst configuration, can you tell us what the best is?
Of course, Naitik, when possible, the closed loop is the best configuration for your air system. If you look at the closed loop illustration, you will see no matter where the air drops are located, there are always two sources available to feed them. This feature of the closed loop system has several advantages. The first is that the air restriction is reduced by half. In some cases, you could even afford to use a slightly smaller diameter pipe to satisfy the same demand. The second advantage of a closed loop system is the ability to isolate sections of the network when performing planned maintenance. If you have taken the trouble when planning to divide your loop into sections with shutoff valves, you will be able to isolate limited parts of your system for maintenance. During this time, the rest of the system will still receive airflow. This allows you to respond to emergencies, perform maintenance, and not interrupt your other activities. This is a major benefit of designing your system in a closed loop. The third advantage, and not least, is the possibility of having a uniform pressure throughout your system.
The next step in properly planning your system is crucial. It involves you determining the diameter of the pipes to be used. To establish the diameter of the header, you need to calculate its total length and the total volume required. Then, to size the diameter of each drop, you must establish the required length and volume of air as you would in a linear system configuration. This chart helps you select the diameter of the pipes in a closed-loop system. On the left, you have SCFM, and on the top, you have linear feet. To use the table, simply select the row that corresponds to your SCFM requirement and select the column that corresponds to the total length of the main loop in linear feet. The diameter can be found at the junction of your row and column. Note that this data is recommended by the Compressed Air and Gas Institute in order to obtain an efficient system. Andrew, can you give us an example?
We have a closed-loop system of 600 linear feet on which we want to add 25 pneumatic tools that together kind of total up to 480 SCFM. Looking at the table, we take the column that corresponds to 600 feet, which is the entire length of the system. Then we select the 500 SCFM line because it is the closest rounded up value to our air requirement. At the intersection of the column and the line, we arrive at a result of 50 millimeters for the diameter of our pipe. However, according to the table, 50 millimeters will only meet our current needs. In a case like this, we recommend selecting a larger diameter, 63 millimeter. The reason why we recommend selecting a larger diameter, in our example, 50 millimeter only meets current needs and offers little flexibility if our consumption requirements increase. Most people tend to plan for their immediate needs and will face a problem when an expansion project comes along or the demand for air increases over time. Let us take a look at this comparison. In our example, it was recommended that you use 63 millimeter pipe instead of 50 millimeter. The 63 millimeter pipe costs 25% more. However, the gain in capacity is 90%. So it is a little bit more expensive up front, but it is a lot cheaper than having to replace your 50 millimeter pipe in a few years or having to run a second line. That is why it is recommended to size up the main line during the planning stage to account for future expansion. When a closed loop is not possible, you have to design a linear network. You calculate its diameter using the same methodology, however, using the table for a linear network. This same table will also be used to determine the diameter of your drops, regardless of the configuration of the main system.
Once the diameter is determined, it is important to take into account the thermal variations of your system. There are certain areas where the compressed air is not at the same temperature as the ambient air, which can cause deformation in your pipes. You will have to determine areas that will allow your airline to expand and contract without undue stress. Andrew, can you explain how this phenomenon can be controlled?
Of course. The configuration we see most often to absorb expansion is the expansion loop. This involves using 4 elbows to form a U shape that will allow us to create what we call an elastic element in the piping. In the case of Topring's PPS range, for example, an elastic element is required for each continuous line of 50 meters, which is 164 feet or so. So, as soon as you have a line of piping that equals or exceeds 50 meters in a straight line, you need to plan for an elastic element like an expansion loop. For example, if a pipe in a fitting connection is installed too close to a wall, say a 90-degree bend, and there is expansion or contraction due to thermal variations, this will misalign the pipe and affect the connection.
Another variable you should consider is the vibration generated by your compressor. The best way to mitigate this effect is to use an anti-vibration hose. It's essential to add this protective barrier between each compressor and the beginning of your system. The vibration may cause excessive wear and tear.
Now let us move on to planning the slopes in your system. In most installations, we often plan for an air dryer. Theoretically, we assume that there will be no water or liquid buildup in our system. Nevertheless, it is a good idea to provide an extra safeguard in case your dryer fails. The rule of thumb is to give the main piping a minimum slope of 1%. Now, obviously, if you have a 1,000-foot long system, creating a 1% slope would result in a significant drop in grade from one end to the other. You can break it up into several sections and install drainage drops at the bottom of each slope.
And finally, what would a pipe be without its mounting clips? It is essential to have a sufficient number of mounting clips. All piping systems have different fastening requirements. With Topring's PPS piping system, it is strongly recommended that the brackets be spaced between 5 and 13 feet apart, depending on the ambient temperature and the diameter of the pipe being used, but always at 8 inches from the fitting or takeoff drop coupling. This measure ensures that the pipe can slide in its support and move freely as a result of expansion. You are now aware of the advantages of the different materials used in the design of compressed air systems. You also are better equipped to start planning your own project. Now we would like to introduce you to Topring's PPS piping system. The PPS system is a 100% aluminum solution, which means that it has all advantages we discussed earlier in the training: corrosion resistance, lightweight, smooth interior finish, optimal airtight sealing, modular design, no threading, no soldering, and a much lower installation cost than steel and copper. The entire PPS system has a maximum operating pressure of 232 psi or 16 bar and an operating temperature range of -20°C to +80°C. The PPS pipe series is available in 9 different diameters ranging from 16 to 100 millimeters. The extruded pipes are made of an anodized aluminum alloy ENAW6063. They are calibrated, and the seamless manufacturing process results in a quality extrusion. The pipes are coated with the blue ROHS compliant electrostatic paint. Each pipe is identified with the specifications and has a dotted line for easy alignment during assembly.
The PPS fitting has an aluminum body with a compression nut. A stainless steel spacer ring grips the pipe and provides high retention force. A lubricated double lobe seal keeps the fitting tight even under difficult conditions. The seal is made of a Teflon-coated nitrile rubber. It is chemically stable and does not easily deteriorate over time. This ensures that it will remain airtight for a long time.
The connection for the 100 mm diameter has a special feature. We find the same internal components, but the installation is different. Rather than using a large compression nut, the 100 mm fitting is held together by 3 hexagonal head bolts. Also, in the 63, 80, and 100 mm diameters, we have the option of an ANC universal connection flange to connect the network to a compressor, a drawer, or an existing network. The flange swivels for an easy alignment when connecting, and it fits both an ANC and DIN flange. The lubricated double lobe seal secures the connection with the tube. The seal between the flanges is secured by a flat gasket with concentric grooves made in NBR, also known as nitrile bunion rubber coated in PTFE, or commonly known as Teflon. One of the most innovative features of the system is the PPS takeoff drop coupling. There may occasionally be condensate in your system. In the event any water is present in the main line, you don't want it to reach the takeoff drops and applications. This is why it is important to not draw air from the bottom of the line, but rather from the side or the top. In the past, this used to be done using a gooseneck technique. This technique consists of cutting the line, installing a T pointing upwards, raising the drop a few inches, adding an elbow to return to the horizontal position, then a second elbow to return to the vertical position, and then the drop. So, to install a single airdrop, it required 3 fittings and a lot of work. It was time-consuming and labor-intensive. On the other hand, the PPS takeoff drop coupling does the same job without all the extra steps. Its internal geometry takes air from the side of the pipe, letting the condensate stay at the bottom of the main line. The couplings hook around the main pipe, so there is no need to cut the main pipe to install a drop. This results in a significant advantage in speed of installation, accuracy of drop alignment, and ease of future modifications. Because of these features, it is a major advantage for a network construction.
Another advantage is that the drop coupling is very compact compared to that gooseneck. It points the pipe directly in the desired direction, so there is no need for a few inches of clearance at the top of the pipe.
And drop couplings are an excellent choice if you want to create a horizontal, intermediate line with your main system.
This sums up all the advantages of our pipes, fittings, and drops, not to mention the general appearance of the Topring PPS network, which looks much better than the other materials. The PPS series possesses several certifications required to comply with industry standards. The pipes, the fittings, the safety lockout valves are all CRN registered, which is your Canadian registration number. This important certification is valid throughout all Canadian provinces. In Canada, all piping over 3/4 inch in diameter is regulated by standards. In Ontario, the TSSA establishes these standards. It is an essential to use certified components to build a system larger than 20 millimeter or 3/4 inch. In addition to the CRN, the PPS system possesses several other certifications that are displayed on the screen.
This concludes this training session, and we hope you've enjoyed and understood the importance of properly planning a compressed air network. If you have any questions or need assistance or advice for your projects, we invite you to schedule a meeting with us by clicking on the link at the bottom of the training page. Thank you, Andrew.
And thank you, Naitik.